Hi, today we're presenting to you our recent work on adversarial robustness under long-tailed distribution. Deep neural networks are usually found vulnerable to minor adversarial perturbations. This problem has been widely recognized and extensively studied in recent years. Most existing works on the basic studies of the classification task are conducted on balanced datasets, such as CIFAR and ImageNet. Among them, CIFAR is probably the most popular playground. However, real-world data are usually not ideally balanced. Instead, they often exhibit a long-tailed distribution. This brings challenges not only to the pure recognition tasks but also to the robustness against adversarial attacks. The second problem remains largely unexplored, and it is the initial motivation for this project. In this work, we would like to leverage the manually created long-tailed versions of CIFAR 10 and CIFAR 100 datasets for the main parts of our experiments. We also provide some preliminary results on ImageNet LT in the supplementary. The basic defense framework we use in the paper is adversarial training, one of the most effective and widely used methods. The standard adversarial training and its variants can be formulated as a minimax problem like this. And we would further show how to extend it to better meet a long-tailed distribution. Let's start from the baseline experiments. Plain models without defense provide the results shown here. For a long-tailed version of CIFAR 10, the natural accuracy decreases from head to tail. When adversarial training is applied, the natural accuracy for both datasets drop to some extent, and both natural and robust accuracy observe a sharper decline for the tail classes in the right. And the overall performance is far from being desirable. Hence, we seek help from the long-tailed recognition methods. Here we summarize some typical methods and categorized into 3 phases based on different applying stages, namely training stage, fine-tuning stage, and inference stage. As shown in the table, we reformulate them in a way that can be naturally combined with the adversarial training framework. We summarize some of the key observations and knowledge revealed by the empirical study. The first is that natural accuracy is easy to improve. A number of LT strategies are proved effective, as marked in green. In comparison, robust accuracy is relatively stable and hardly sees a large improvement. But we notice that classifier normalization and rescaling achieve impressive robust accuracy under PGD attack, as marked in red, while the auto attack evaluated results remain ordinary. We denote this by a fake improvement caused by unreliable robust accuracy. Specifically, the false sense of security is not new knowledge. We clarify that there are 2 terms of it, namely gradient vanishing caused by logit stretching, and direction averaging caused by logit compressing. Classifier rescaling-based methods suffer from the latter. Finally, in order to obtain a stronger robustness, it is critical to keep a low boundary error, or the gap between natural and robust accuracy. And the basic cosine classifier appears to benefit from this, marked in blue. The cosine classifier addresses the problem of imbalanced boundary caused by difference in classifier norms, and it alleviates the risk of being attacked through feature scaling, especially when boundary adjustment have already been conducted. Thus, we adopt a variant of it to our method. Except for the classifier, we design a 2-stage rebalancing strategy. At training time, we design a class-aware and pair-aware margin, and we also include a regularization term following trades. At inference time, we adopt a class-specific bias to further address the larger feature deviation for tail classes. Please refer to our paper for more detailed deductions. For the experiments, besides the long-tail methods with adversarial training in our study, we compared with several SOTA defense methods and achieved superior performance. We also provide the per-class recall on CIFAR 10 and show how we're trying to narrow the gap between the performance of the ideal full dataset and its long-tailed version. The method is also proved effective under different imbalance ratios. Please refer to our paper for more experimental results. An overall comparison is provided here. In summary, we first propose a challenging and realistic new task that tackles adversarial robustness under long-tailed distribution, along with a systematic study and a clean yet effective method. This is an interesting attempt towards real-world robustness and leaves a lot more to explore in the future works. Our code is available on GitHub, including all the long-tail methods with adversarial training mentioned above and several other extensions. Thanks for listening.